In this video, we'll discuss how you can solve limits of a function that give you an indeterminate form. So that's like 0 over 0 or infinity over 0. And there's this whole algebraic method or using conjugate that you can do to solve for this limit when you're given an indeterminate form. However, what's a more quicker and faster way to solve this limit without having to do all that? And that is L'Hopital's rule. L'Hopital's rule basically states that the limit of a function, right? So you can have f of x over g of x is equal to the limit of f prime of x over g of x over g prime of x. And when you do this, you're able to basically loop around this indeterminate form and solve the limit. And sometimes finding the first derivative of your function may not yield the solution to your limit. So sometimes you may have to find a double derivative of your function, right? So f double prime of x over g double prime of x. And you can keep doing this so on and so on and so on because L'Hopital found that they're essentially equal to each other and that they will give you your answer to your limit and bypass the indeterminate form. So let's take a look at some examples using L'Hopital's rule. First example, we see that limit as x approaches 2 for this function, right? However, we notice, right, that we can quickly determine that this is going to be an indeterminate form, right? So, right, but before we have to show that, especially if you're writing an FRQ. So in this case, we'll break down this fraction into two parts. So we'll have our numerator and then our denominator. So f of x is going to be set to the numerator, right? So we're going to have 2 plus x inside our root minus 2, right? That's the whole numerator. And then we'll have the denominator, right? Right. And when you're writing an FRQ, you need to make sure you establish that these functions are continuous, right? So we know that these functions are continuous, right? We know they're continuous because you can imagine this has a slope of 1, so this just keeps on going linear, right? Same with this, where we know that this has no domain restrictions, so it's continuous, right? We've already established that. Nice, right? Okay, and then we need to know that when we plug in 2, it equals 0. So let's do it up here, right? When we have f of 2, right? When we plug in 2 into this numerator part, we'll have 2 plus 2, which is going to be 4, and then the root of 4 is 2. So we have 2 minus 2 is going to be 0, right? So then we set this equal to 0, right? And then g of 2, right? When we plug in 2 into this bottom part, 2 minus 2 is going to be 0. So there we go. We've established that it is indeterminate here, right? So since we've established this, we can say then by L'Hopital's rule, L'Hopital's rule, right? We can say that the limit as x approaches 2 for root 2 plus x minus 2 over x minus 2 is going to be equal to the same thing as limit of x approaches 2, right? And we're going to do the derivative of f of x and g of x. So we know that g prime of x is going to be equal, right? So we have a radical, right? And you've probably already memorized this, like this standard form for this part, which is just going to be root or 1 over 2 root, and then what's in the inside, 2 plus x. And then because this is a two-part inside of each other, we'll use chain rule. And we know that the derivative of the inside is just going to be 1 because this is a constant, which is going to be 0, 0 plus x. And the derivative of x is just 1, so we'll multiply the whole thing by 1. Which we know that anything multiplied by 1 is just itself, so we don't have to write that down. So then we do the derivative of g of x, right? And we know that, right, the same thing we applied inside of f of x, we'll apply to g of x, which is going to be equal to 1, right? So then it's going to be equal to f f prime of x over g prime of x, which can be represented as limit as x approaches 2 for 1 over 2 root 2 plus x over 1, right? And I'm going to move a bit so we need some more room. Okay, this is good, right? Okay, and then now we can plug in 2, right? But since this is all over 1, we don't really have to write this, so it's less confusing, right? We have this. Now we can plug in 2, right? Make sure I write that. Right, so 1 over 2 root 2 plus 2, right? We know this 2 plus 2 is going to be 4, and we know that the root of 4 is just 2, and then 2 times 2 is going to be 4. So this is 1 over 4. And that is our answer to our limit. Let's take a look at this example here, right? So here we see we have a one-sided limit as it approaches the right side, right? But don't freak out. It's not as hard as you may think it is, right? And then we also see some trig, right? We see cosecant and cotangent, right? Right, but you should have learned, you should be familiar with your trigonometric functions from pre-calc, right? So don't fear, right? So we can already know that we're going to use L'Hopital's rule for this example, right? So we can break this limit into, or this function into two parts, right? So then numerator, right, is going cosecant of f of x, and g of x is equal to the denominator, which is cotangent of x, right? And then we're going to clarify that these two functions are continuous, right? Both this one and that one, right? They're both continuous, right? Oops, okay, right? They're both continuous. However, we know that when we plug in pi, right? When we plug in pi into cosecant, so let's do that right now, right? So f of x and then pi into cosecant. Let me write that better, right? We have cosecant of pi. Right? This can be written as 1 over sine of pi, right? And we know that when at pi, right, cosine is -1 and sine is 0. So we would get something like 1 over 0, right? Which is incorrect. And therefore, right, we don't have to worry. So just make sure you establish that on your FRQ, right? And we'll do the same thing for the denominator, right? 1 plus cosine, 1 plus plus cotangent of pi is going to be equal to 1 plus, right? And then you know that tangent, right? Tangent is equal to sine of x over cosine of x, right? You're changing y over you're changing x, right? That's your tangent. And then your cotangent is essentially your reciprocal, right? Your cotangent is the reciprocal of tangent of x. So we're basically going to switch sine of x around with cosine, right? That's what we're doing when we have cotangent. So now we have cosine of pi over sine of pi, right? And as we know here, this is going to be 0. We're going to divide by 0, so it's just going to be 0, right? Because we know that sine of pi is going to be 0, so it's not going to work out, right? So now that we've established that this does not work out, right, we can use L'Hopital's rule. So by L'Hopital's by L'Hopital's rule, right, we have the limit as x approaches pi on the positive side of cosecant, or my bad, of cosecant of x over 1 plus cotangent of x is going to be equal to the derivative of f of x and g of x. So we can find that by finding f prime of x, right? So f prime of x is going to be equal, right? So from your trig identities for derivatives, we know that the derivative of cosecant is going to be negative cosecant x times cotangent of x, right? And the derivative of the denominator g of x is going to be equal to 1, right? This is a constant, so we don't have to worry about that. We don't have to write that out. It's going to be the derivative of cosecant is going to be negative cosecant squared of x, right? And then we can write this all out, right? And then we know that when we have when we're dividing two negatives, it's going to be a positive, so we don't have to worry about the negative here. So limit as x approaches pi on the right side of cosecant of x times cotangent of x, right? And then here, right, we see cosecant squared, which is essentially the same thing as cosecant x times cosecant of x. And we can see that these can cancel, and we're left with cotangent of x over cosecant, right? And we can also rewrite that differently. So if I make enough room, okay. So we can write this as, right, cosecant or cotangent is going to be equal to cosine of x over cosine of x over sine of x. And it's all going to be over 1 over sine of x. All right. Okay. Let me make some more room. Okay. Okay. We see this. All right. So we have limit. Now that I've made some more room, we can keep carrying this out. All right. So we have the limit as x approaches pi, and we can write this, right? Because keep change. Right. So we have cosecant of x over, or my bad, not cosecant. Cosine, right? So we have cosine over sine of x times sine, right? Because we do the reciprocal of this when we go from division, right? From division to multiplication, right? And right, we can also write this down, and then we can set sine of x over 1 because that's still the same thing as just sine of x, right? But now we have a sign on the numerator and a sign on the denominator. And because we have that, we know that they can cancel. So therefore, we're left with limit as x approaches pi, the positive side, of cosine of x, right? Now we can plug in pi. So we can have cosine of pi. And then we know that cosine of pi is just equal to -1, right? And this is your answer to your limit. All right, let's take a look at this example. So here in this example, we have h of x, right? And we have this function, right? For this function only works, right? We have f of x only works when x is not equal to 2, right? And we're trying to evaluate, or we're trying to find these function values, right? When we plug in 2. So, and we're given h of 2 is equal to 4. So we can still evaluate this using L'Hopital's rule. Although it does look a bit more complicated, it can still work out. So we're going to separate h of x into two separate functions. We have h of x into the numerator, -4, and then g of x is going to be 1 minus f of x cubed. All right. And we're trying to find this function value, and we know that when we plug in 2 into this value, we're going to get 0, right? So we can set this equal to as a limit. So as x approaches 2 for x squared minus 4, this does not work out, right? Because not only does this not work out, but it also tells us it won't work out. So this is going to be 0, right? And then the same thing is going to happen when we approach 0 for the denominator, right? So, I mean, as we approach 2, my bad. So when we approach 2 for the denominator, 1 minus f of x cubed is going to be equal to 0, right? It has to be equal to 0. And we have 1 minus f of x cubed is equal to 0, right? And we're trying to find uh, the value of f2, right, when we plug in 2 into f of x. And we know that when we approach it, we get 0. So what can in other words, we can write this as f2 of cube is equal to 0, right? Because when we're approaching this, we should get 0, right? And that's what we have here. And this is what it tells us. It has to be equal to 0 right here. This tells us that. So what is a value that when we subtract 1 will give us 0? So 1 minus 1 has to give us 0, right? So only 1, right? Because 1 minus 1 will only give us 0. So therefore f of 2 has to be 1. And 1 cube won't be affected because it's just 1. 1 times anything, it's itself, and therefore 1 is itself. So 1 minus 1 is 0. Right, so now that we have the function value for f of x, now we have to find the function value for f prime of x, right? And we can find that by using L'Hopital's rule. Because they're continuous, right, we can say by L'Hopital's rule, right? Because by L'Hopital's rule, we know that the limit as x approaches 2 for f of x over g of x is going to be equal to the limit as x approaches 2 for f prime of x over g prime of x. So because we have these function values, right, we have these functions, we can just find the derivative, right? So we have f of x, f prime of x, right, and we're going to use power root because we just have to carry this, right, because we know this is a constant, so there's just going to be 0. So I have 2x, and then g prime of x is going to be equal to, right? And then we have a constant, so that's going to be 0. So we don't have to worry about that, right? So we know we can carry this. We can treat this similar to how we set this equal to a when we found this, or not similar to how we set this equal to. We can just substitute this as x. We can think of f of x equal to x. And we can continue to apply power rule here. So we can carry down the 3 and subtract the exponent by 1, and therefore we have this, right? So now that we have this, we can just do the limit, and therefore now that we have this, right, we can just set this, the limit as x approaches 2 is going to be equal to 2x over 3x squared, right? And we previously were told that h of 2 is equal to 4, right? So we know that this has to be equal to 4, right? This has to be equal to 4, right? Now let's move this a bit, right? Okay, right, because this has to be equal to 4, we know that when we plug into, right, when we plug into, this has to be equal to 4. So we know that this is 4, right? And therefore this has to be 1, so this can follow, so so this can follow what we were told previously. So now that we know that the numerator is equal to 4 and the denominator has to be equal to 1 to follow this, right? We can just set this equal to, we can set the denominator equal to 1 and have an algebraic problem. So 3x squared equal to 1, right? And we're trying to solve for x. We're going to divide by 3 and then do the root of everything. And therefore, we go back here. This, when we plug in this, it has to be equal to 1, or the root of 1 over 3. And these are our answers. Let's take a look at this problem, right? So we have the limit as x approaches 0, and we can break this limit into 2 parts. So we can have f of x set equal to the numerator, so we have that sine of 2 of x minus 2x. and we'll have the denominator equal to g of x, right? So we have that. And we know these are continuous, right? Because I'm pretty sure, at least you should have seen a sine graph, right? And you should have seen a cubic graph. So therefore uh, we can state that these, we'll write that a bit further, are both continuous, right? They're both continuous. And we know that when we plug in 0, right, we're just going to get 0, right? Everything's going to be 0. There's going to be 0 minus 0, and x cubed is just going to be 0, right? So we don't even have to plug it in. We don't have to plug in 0 into x to know that it's going to be 0, because we know that literally anytime we have 0, it's just going to be 0. So therefore, we stated that it's continuous. We stated that they're equal to 0. Now we can use L'Hopital's rule, right? So we can state by L'Hopital's rule, we have the limit as x approaches 0 of sine of 2 of x minus 2 of x and be equal to x cubed, right? And we know that this is equal to the limit of as x approaches 0 is going to be equal to f prime of x over g prime of x, right? And now that we have this stated, we can find the derivative of the functions. So we have f prime of x, right? And we know that the derivative of sine is just going to be equal to cosine, and then we plug in what's inside, 2x, and then we use what's outside, times 2. So we just put the 2 on here, right? And then minus 2, right? Because we use power rule to find the derivative of 2x, right? And now we have our derivative for f of x. Now let's find our derivative for g of x, which is pretty simple because it's just x cubed, right? And we're going to carry down the exponent and subtract the exponent by 1, which is going to be this. And therefore, we can write this as the limit as x approaches 0 for x cosine of 2 of x minus 2 all over 3 times x squared. Right. However, you'll notice that when we do this, this still doesn't allow us to evaluate, right? Because if we plug in, right, we plug in 0, where we'll plug in. Let's separate this limit, right, this thing, into 2 parts as we previously did, right? So we'll have f of x. Actually, we'll plug in 0. We'll plug in 0 into f of x. This is going to be our numerator. So we have 2 cosine times 2 times 0 minus 2. And we'll do the same thing for the denominator, right? We'll plug in 0 for the denominator, and we'll set that equal to g of x. 3 times 0 squared. Okay, so let's do the simple part. We know that 0 squared is 0, and 3 times 0 is just going to be 0, because anything times 0 is just 0. Right, and we'll have 2 times cosine, which is going to be 2 cosine of 0 minus 2. Right, and then when we have cosine of 0, we know that cosine of 0 is going to be 1. So we have 2 times 1 minus 2, and that is just 0. So, right, we have this. Let me make some more room. Okay. There we go. So we know that both of these functions are continuous. So we can state, we'll write it down here. Both functions, let me write that a bit better. Both functions are continuous, right? They're both continuous, right? And they're both continuous and they both equal 0. We can continue to apply L'Hopital's rule. So now we're going to find a double derivative of these functions. So we're going to do double derivative, right? Because L'Hopital's rule states, or before I do that, let's explain. So we know that L'Hopital's rule states that the original limit is going to be equal to f prime of x over g prime of x, and it can continue on forward. So we can even say that f double prime of x is f double prime of x over g double prime of x is still equal to the original f of x over g of x. So we can continue to apply this, right? Oops. X approaches 0 is going to be equal to f double prime of x over g double prime of x. Now we can find this, right? So we have 2 cosine of 2x, right? And we know that the derivative of cosine is going to be negative sign, so we'll have negative. Or first, we got to remember, we still got to carry this 2 out, so it's still going to be negative 2 sine, and plug in the inside, all multiplied by 2, right? Because we do the derivative of the inside, which we can just multiply this 2 and be 4 sine of 2 of x. And we'll do the same thing for g. Find g double prime of x. And we know that when we apply power, this is going to be 6x, right? Bring down the exponent, multiply it by the coefficient, and then subtract it by 1. And that's, we continue to see that even if we plug in, here, we'll make some more room. We continue to see that if we plug in, right, so we have this, right, and we plug in 0, we can imagine that this will give us 0 over 0. It still continues to be indeterminate, right? So we can continue to apply L'Hopital's rule. But, right, before we can do that, right, we got to think back that we're writing, or we're acting as if we were writing the FRQ, so we got to demonstrate that this is still, in fact, indeterminate. So we can still write this, well, we'll separate this limit into 2 parts, into our numerator equal to f of x is going to be negative 4 sine of 2x, and g of x over 6x, right? So we know when we plug in 0, we know that 6 times 0 is going to be 0, right? We know that. And negative 4 times sine of 2 times 0, which is just sine of 0, is going to be 0, right? So negative 4 times 0 is going to be 0, right? And we can continue to say that both functions, right, both f of x and g of x are continuous. They're both continuous, right? And now that we know that they're still indeterminate and they're still continuous, right, we can still continue to say that by L'Hopital's rule, the limit as x approaches 0 is still equal to f triple prime of x over g triple prime of x. So therefore, we can find the triple prime of f of x, so f triple prime of x. So therefore, we can find the so therefore we have to find the derivative of f triple prime of x, and we'll find that by applying chain rule. So we have negative 4 cosine, right? Negative 4 cosine times 2, right? And then we can still multiply this, or multiply this, right? So we can rewrite this as negative 8 cosine of 2 of x, right? And we can find g triple prime of x is going to be 6, right? That's that. And then we're actually going to bring this down just because we're running out of, so we have, bring that down here. So we have the limit as x approaches 0, right? And we have this, so we have negative 8 cosine of 2 of x all over 6. And therefore, now we can plug in 0 into x. So negative 8 cosine of 2 times 0 over 6. right? And then we're going to bring this down a bit. Here, make a bit of room. Okay, we know that this is going to be equal to negative 8 times cosine of 0 over 6, right? And we know that this is going to be negative 8, and then cosine of 0 is just 1, right? So we have negative 8 times 1 over 6, and it's just negative 8 over 6, which you could also simplify into negative 4 over 3, and that is our answer for our limit. Although this process was very tiring and it took us a lot of math to do, it still allowed us to get our answer much more easier than it would have to do it a different way, like algebraically or using conjugate. And it truly shows the beauty of L'Hopital's rule and how efficient L'Hopital is, right? Uh, Although the FRQs does make the process of using L'Hopital's rule very tedious, you can apply L'Hopital's rule with an MCQ, and it just is so much more easier to use and faster, quicker, and saves you a lot of time, especially during test taking. If you did enjoy this video, please make sure to consider subscribing. If you have any questions or any concerns, please make sure to comment. Yeah, until next time, thank you. And yep, thank you. Adios, amigo.